Thank you. First slide. I first was introduced to fractal geometry a year ago in Potsdam at the last conference. Recently, since I'm going to talk about geometry, I'll just very quickly review the basic geometry we're looking at. We have to, for most of these gas-solid reactions, consider the solid, the pore space or the void space, and the interface itself as a separate entity. Over the last couple of years, there have been several papers by people like David Abney and Peter Pfeiffer, where they have applied, or tried to apply the principles of fractal geometry to catalyst systems and porous solids. We can turn that off for a minute. Basically, if you consider a straight line as a representative picture of a flat surface, we can consider the red and blue spheres, if you like, as being different sized adsorbates on the surface. And it's possible that, well, you consider n as being the number of disks of radius r necessary to measure the length of this line, that one can derive a relationship between n and r. n is proportional to r to the minus 1. Regardless of which adsorbate we use, for a straight line, you'll get the same length measurement of this line. However, it changes slightly when you have a rough or rugged or a porous surface to consider. Here again, it's on geometric principles. The surface area, for example, as measured by the red or smaller adsorbates, would be expected to be higher than the surface area as measured by the blue, the larger adsorbates. And there are relationships derived based on fractal geometry. And basically, an object is described as a fractal or a fractal surface, if you like, if the rate of occurrence of new features of irregularity is governed by this sort of power law, and is proportional to r to the minus d. D in this case is a fractal dimension of a line or a curve. And again, for lines, d would vary between 1 and 2, corresponding to a 1 dimension and 2 dimension. And for a surface, d varies between 2 and 3, corresponding to, say, a 2 dimension and 3 dimension surface. And I think we'll go back to the slide. So we took some data of a syncrude coke, which is a coke produced by fluid coating of alphabasket bitumen from the syncrude plant in Fort McMurray, Alberta. The coke was separated, as we see, into several particle sizes, ranging from I think 24 to almost 1,000 microns in diameter. And if we look at areas, surface areas measured by nitrogen, DET, or measured by CO2, DET, we can see that the surface area is approaching infinity as you go to smaller and smaller particle radius in this case. The surface areas were determined on a Carlo-Urban instrument. Nitrogen areas at 77K with BET plots. The CO2 was determined at 195K. And we use both BET and Dubin's equations to calculate surface areas. Now, on the work of Abney and Pfeiffer and their co-workers, they came up with several relationships. In this case, between the monolayer mole number and the effective cross-sectional area of an adsorbate. The top monolayer mole number is proportional to sigma, the effective cross-sectional area, to the power minus d over 2. Again, minus d is the fractal dimension. And considering a specific surface area, the apparent surface area A is related to sigma to the power 2 minus d over 2. It's not my intention to derive any of these equations. We try to find a use for them. Similarly, they went through and described a series of experiments using one adsorbate and several particle sizes of an adsorbent. And again, they derived equations, n proportional to r, capital R, but that's the particle radius, to the power d minus 3. And the same equation for current surface area A, proportional to r to d minus 3. It's obvious from the bottom equation, for example, that when d is 3, the surface area is dependent on particle size, which is the case with most of the catalysts that I was used to working with. And again, Abner has derived equations relating these four that I've shown up here. So we took the data and plotted it. For example, this is the CO2 surface area data plotted against particle radius in a log-log plot. And whether we used BET or Dubinin sort of equations, we were getting similar straight lines. And it covered most of the particle size range that we had looked at. From the slope of these curves, if we consider equation 4, the slope is equal to d minus 3, and we were able to derive the d value. Obviously, from here, you can see the relationship between the BET and the Dubinin plots as well. Both plots provided a value for d, fractal dimension, of 2.48. Similarly, the nitrogen data can be plotted the same way. Now, unfortunately, the nitrogen data is ranging from about 1 to 15 square meters per gram, and perhaps not quite as reliable at the low end, particularly. And it covers a smaller particle size range than does the CO2 data. But the d value calculated from this slope of the log-log plot was 2.38, which is very similar to the CO2 data. One of the reasons we were looking at these surface area measurements of cold samples is that in our laboratory we are involved in a lot of work in, say, coal and char combustion or coal liquefaction, where obviously the rates of these reactions are going to be dependent upon things like the accessibility of the active sites on the surface. So one of the things I wanted to look at after finding the fractal dimension from gas absorption data was to see if I could derive the same equation from some other data. We looked at mercury pore symmetry in the same ranges on a conventional micromagnetic porosimeter. And again, we see this relationship. The pore volume in this case is increasing with decreasing particle size. This is almost a linear relationship, so it's no surprise that the log-log plot is also linear. And we can derive, if we use the same equation 4 that I showed earlier, we can derive a value for fractal dimension of this syncrude coke based on mercury porosity data. And in this particular case, I think it was 2.53. I have the table later on and we'll look at it. So we're deriving the same fractal dimension, the same description of surface roughness from mercury porosity data. And we looked at the rate of oxygen absorption on these same coke samples. And if we plot the rate as grams per gram minute, for example, the top line, against particle radius on a log-log plot, we again come up with the same value of the fractal dimension. In this case, the oxygen absorption experiments were conducted on a thermal balance at 200 degrees C in a slowing atmosphere. And we're measuring the weight gain with time. And the rate expressed here is the rate of what was the second stage of oxygen adsorption. There's a very rapid initial oxygen absorption and then a very slow linear absorption with time. So this is the second linear rate. And again, for the same syncrude coke samples, only over different particle size range now, we're deriving the same fractal dimension. Here's a summary of that work. We consider nitrogen, CO2 adsorption, physical adsorption, the oxygen adsorption data, and the mercury porosity data over the various particle size ranges that are listed up here. And we can see the fractal dimension varying from 2.38 to 2.53 for the oxygen gas. And I thought it was very nice to derive the same fractal dimension for these species by the different adsorption experiments and by nutrient pore symmetry. One of the problems, I think, demonstrated by Dr. Dahlman just recently, that a lot of this work depends on what one chooses for the sigma value of the effective cross-sectional radius, if you like, of the adsorbate. And it certainly doesn't explain all of the phenomena which is occurring in gas absorption, for example. It is more of a geometric interpretation of some of the results. I went on a little bit further after doing this work to look at the reactivity, gasification reactivity of various coal samples. Again, using different particle size, over approximately the same range of particle size. And in this case, we're looking at the reactivity is the weight loss, the rate of weight loss at 900 degrees C in an oxygen atmosphere for, in this case, 4 different coal samples. And again, it is possible to say that the rate of this reaction is proportional to the interface, if you like. And when we plot log of reactivity, or log of rate, against log of radius, particle radius, we can derive a fractal dimension from these plots. And of the 4 coals tested here, the fractal dimension does vary from 2 to 3. I can't remember exactly what they were. But what we were trying to explore is the possibility of predicting the rates of, or the reactivity, if you like, of the various coal samples based upon a geometric interpretation and based upon their fractal dimension. Again, unfortunately, this is rather a simplifying approach because there's several other factors involved in all of these processes. But I think we achieved what we started out to do, and that was to show some of the applications of fractal geometry, particularly in areas where we were working, areas where perhaps the reaction rates we were looking at were dependent upon the interfacial area of the various coal and coke samples we were looking at. We still get back to the initial problem, the difference between surface area, for example, BET surface area, measured by nitrogen and by CO2. And you can see that both nitrogen and CO2 surface areas increase. What they were doing was increasing with decreasing particle size. And we reached the point where the nitrogen areas peaked, and the nitrogen areas then fell back down from about 15 to 20 square meters down to about 10, 11, 12 square meters. This occurred at about particle size of around 70 micron diameter. The CO2 surface areas continued to increase with decreasing particle size. And while we found the fractal dimension useful for some of our studies, it still doesn't explain the processes that are occurring. It does give us a convenient parameter to compare 2 coke samples, for example, things of this nature. But it still doesn't explain all of the absorption problems. For example, I think it's been described that nitrogen surface area may measure, say, macropore and mesopore areas, whereas the CO2 is measuring the micropore surface area. And there are some theories about activated adsorption and so on to try to explain the lower values associated with nitrogen being 2. So we are still left with the original problem, trying to explain the difference between the various adsorbents. One thing I should point out is that the samples we used, the syncrude coke, was used as received, and all of the various fractions had exactly identical chemical composition. Again, it's something that you would expect if it was a fractal surface, that the various particle sizes would have to be identical geometrically and chemically. And what we found in our chemical analysis and things like helium density, carbon, hydrogen content, and what have you, was that all the particles were identical. This, of course, is not true for all coal samples. It happened to work out very nicely in the case of the syncrude coke that we were using. And one of the basic theories of fractal geometry was the assumption that the processes which formed these substances were iterative processes, where either, in our particular case, the coke particles were built up in the fluid bed coking reactor by bitumen adsorbing onto a nucleus, the volatiles coming off, leaving a coke surface. I don't have the SEM pictures to show you, but when we looked at the particles under the SEM, they were in fact, it looked sort of like annular rings of carbon going out from a nucleus. The surface of the particle was very smooth. And there are areas of fractal analysis where they look at the profile, microscopic profilometry. In this particular case, the profile of the coke that we were using was very smooth. And if one were to do a fractal image analysis, you would find that the fractal dimension of that profile was actually 1 or very, very close to 1 on such a smooth surface. But the fractal dimension as determined by gas adsorption is obviously quite high. It's between 2 and 3, somewhere in the middle. I think I'd like to end by acknowledging the work of my co-workers, C.L. Ng, Alan Palmer, Ed Fremsky, and David Flum, for providing me the samples and the opportunity to come. Thank you.
Discussion. Mark?
That's a very nice piece of work, but I'm a little bit confused. You started out with the derivation in which the size of your coke molecule decreased, but your scaling says everything is the same as scaling. Now you increase the size of the substrate with a fixed probe. Now that isn't the same scaling.
It is if you look at the papers of Avenir, where they have shown how to drive from one to the other.
Well, I'm still questioning that also. You see what I'm talking about?
But yeah, the problem I have is that I have access to nitrogen, say gas volumetric apparatus, but it's very difficult to get a range of different absorbates and do these measurements. It's much easier to get a range of particle size.
Well, I'm going back to look at the scaling law. It says your particles are growing, but that the topography changes as it's growing. I think you'd have to go
again, it wasn't my intention to derive that equation, but it has been derived. I think I might have it.
I think at this point in your lecture, how did you determine your particle radius?
For the smaller sizes, we use filter counter. A filter counter to determine particle range. I did, in fact, do some work with an image analysis system as well, the DAPL system. To confirm.
This is a hydrodynamic radius you're using.
Pardon me?
A hydrodynamic radius.
For most cases. For some of the larger particle sizes, what I was using was an average of the two sieve sizes that we used. I could only run the filter counter to a certain particle size.
I have a question. It would seem that the smaller particles, at least in implication result, the smaller, the 12 or 15 micrometer coke particles, have a finer microstructure than the larger particles. Is that?
Well, one of the things that you can talk about because of the nitrogen and CO2 data is they're both measuring the same geometric principle, maybe at different size ranges. There was something different about the very small particles. They did not fit on the linear regions of form.
Because if it didn't have a different, a finer microstructure, I wouldn't expect it in practice.
Yeah, I think that's the problem with fractal geometry, is you must reach a point at some point where you revert to the Euclidean geometry. We reach the point where there are no more microstructures. that sort of region. But it can't go on indefinitely up to infinity. So there is a point where it reverts from fractal to the Euclidean geometric shape.
A couple of points. First of all, could you explain how you obtain the surface area from your Dubinian analysis? That's the first point. You refer to Dubinian to give surface area. Now, it normally gives micropore volume, of course, unless you use a Tagana type analysis. That's what you did, presumably.
Sorry, that's
So it's a DRK. Okay, that's the first point. Secondly, how did micropore symmetry come into this? What did you use that for specifically?
I was curious to see if we could use another technique, which essentially was supposed to measure the pores rather than the solid surface.
But you referred to that in relation, as I gathered, in relation to microporosity. Now, normally one wouldn't think about microporosity.
That was an unfortunate choice of terms when I made up the graphs. It was the total graph.
It's total porosity.
No.
Okay. Yeah. Now, the last point, just a comment really. The whole question of the interpretation of this kind of analysis. Is it, I wonder, to do with the fact that if one has a sort of, in mathematical terms, a single value function, you can get a correlation. Now, on the other hand, where there are a whole range of parameters which necessarily come into play, but which are not taken into account in a simple analysis like B area and so on, then I think your method shows up the kind of discontinuity in the mathematical trig. Now, is that fair? So it can be of value in that respect.
Yes.
I'm thinking about, you see, the mechanisms of micropore filling and so on, which are, of course, exceedingly complex, which have nothing whatever to do with BT analysis. Now, when you've got a simple mathematical relationship, then you see your direct correlations, as you've shown. Where, however, the thing starts to go adrift because of other parameters which are coming into play, then your analysis shows that up. Is that right?
I think that's right.
One more question.
This particle size you quote there in microns, is why does the ruggedness of the surface vary with the particle size? Usually, I know what that might be. And have you ever thought of doing any scattering experiments like something like X-ray scattering or neutron scattering, direct probe for this dimension or this ruggedness of the surface instead of a more direct way of comparing the scaling parameter with CO2 or the nitrogen to like monolayer coverage with the ruggedness of the surface rather than this empirical relationship of micron size.
With the second part first, they didn't have access to some of the other techniques. Obviously, it would be interesting to look at them. And the first part of the question. I think the application of fractal geometry simply shows that, if you like, the pore structure is much like a pore tree model, which has been proposed for several carbons. And we're not getting an absolute number on from any of the particle size. We're just deriving a fractal dimension to describe all of the particles. Obviously, the surface area that we determine varies with particle size. But the fractal dimension is just a relative or scaling number, if you like. If I had a second Coke sample compared to the syncrude Coke, you might see an obvious difference. Unfortunately, we only had one sample.
Thank you very much. Last